Hey there, physics friends. It's Sean Lally, your instructor here, and today we're going to talk all about Newton's laws. This is the first of two videos. The first video is going to focus on the basics of the three laws of motion, and then the second video will look at some specific cases. So if you're not too interested in the background, or if you think you've got a pretty solid understanding of the three laws of motion, you could probably just skip over this video and jump ahead to the video where we do the solving of problems with free body diagrams and stuff. So, okay, well, let's get going here. So here we have Newton's birthplace in Woolsthorpe, north of London, north of Cambridge in England. Newton was born in 1642. That's the same year Galileo died. He had died a few months earlier in Italy. Newton was born in England and somewhat of a more permissive country, not quite so much in the shadow of the Catholic Church at that point. So Newton had the benefit of not having to deal with the same kinds of issues that Galileo and Copernicus had had decades earlier. Here's an image of Newton painted when I think he was 46 years old. The over on the right is his grave at Westminster Abbey, which is, geez, it was one of the most stunning things you can ever see. It's really pretty amazing. He's buried there amongst royalty and nobility in England. There's his death mask if you're feeling just a little bit morbid. Newton was so famous and still is so famous that he was on the reverse side of the £1 note up until they discontinued the pound note a couple of decades ago. The Yeah, he was actually on the pound note not only for his work in physics, but in fact he was the warden of the British Mint later in his life. There he is, being honored on the 300-year anniversary of publication of Principia. So just a couple of comments to say about the scientific revolution. Scientific revolution is this period thought really in hindsight as being 150 years that went from a big change from geocentrism, an Earth-centered system of dynamics, to heliocentrism, that is, imagining that everything went around the sun. And of course, that's not the full story, really, but that was a big, big leap. So we think of it as starting with Copernicus's publication of De Revolutionibus Orbium Celestium, which is on the revolutions of the celestial orbs in 1543. And then by the end of the 1600s, Newton is, he is really the man in England, and he had published his Principia Mathematica. And really, so by the beginning of the so-called scientific revolution, nobody was a Copernican. Nobody really thought that the Earth went around the sun. And by the end of Newton's life, well, everybody did. So something happened in that 150 years that we now call the scientific revolution. Here it is in 1687. It's the front page of Newton's Principia. Full title was Philosophiae Naturalis Principia Mathematica. It's published in 1687. In this book, he describes many, many things, but specifically the three laws of motion and all of the many mathematical proofs that come about as a result of them. The law of universal gravitation that we'll get to a little bit later, and just a whole host of other things. It is a large tome of knowledge. I'd never recommend that you read it, not even in the English translation, because it just doesn't, it's not the easiest way to learn physics. It wasn't the easiest way to learn physics then, but it's probably the only way. But now it just doesn't translate that well if you don't speak geometry as a second language. So into the laws of motion, which appear within the first few pages of Principia. Here is the first law of motion. Now, Newton wrote it in Latin. It's published in 1687, but there's an early English translation that this comes from. The first law of motion: every body perseveres in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. Okay, what does that mean? Well, in contemporary language, we basically would say object is going to keep doing what it's doing in a straight line unless there's reason for it to do otherwise. And basically that means it's going to stay at rest, or it's going to keep moving at a constant velocity, which is a constant speed in a straight line, unless it's acted on by an unbalanced force. So in other words, if it has no reason to stop, it won't. If it has no reason to start, it won't. We sometimes just call that the law of inertia. A couple of examples for you here. A very simple one. This is kind of a variation on the, there you go. It's a variation on the tablecloth pull. This is something that's kind of similar. Here I have a couple of eggs, and one of them has water inside of it. That one does not have water inside of it. This one does. When I stop it, you'll notice that it keeps going. The water keeps it moving. The water keeps moving inside of it. It's sort of the difference between a raw egg and a hard-boiled egg. That guy there, it stops and it stops. Now here is, my version of the tablecloth pull. I'm actually going to skip ahead because really all I do is a whole lot of chatting here. But let's see. Okay, here we go.
Are you ready, family?
So I'm doing this in front of my family, and I don't know if they were entertained or not, but here we go.
Get set. Wait a minute.
Okay, here we go.
This seems a little problematic here.
Ideally, everything will stay in place when I remove this. Let's see.
On your mark. Get set.
Okay, well, you get the idea. So here's a few things to think about with regard to Newton's first law. How, if you're on a crowded subway or metro, let's imagine that you're standing holding onto a strap. How does your body react when the car takes off? How does your body react when the car comes to a stop? And what do these things have to do with Newton's first law? Of course, these are things that you have all experienced, I imagine, before, so think about that for a few seconds. Similarly, imagine being in a car. What is the actual function of the seatbelt and the shoulder harness? What do they do? What's the purpose of the headrest? What do those things have to do with Newton's first law? The headrest, of course, protects you from most of the effects of whiplash. If you're hit from behind, your head has something of a hinge in the neck, so it tries to stay at rest. And if you have the headrest, of course, then it prevents your head from sort of being whipped backward, or at least what feels like being whipped backward. And here we see the whole point of the seatbelt. Now, on to the second law of motion. This is the mathematical one. In Latin, it is given there as lex 2. In first translation, it is the alteration of motion is ever proportional to the motive force impressed. Alteration of motion was fancy speak for acceleration. It is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. But this can be better expressed as an equation. In other words, an unbalanced force causes an object to accelerate. If you apply a force to an object and that force is unbalanced, meaning that your force is greater than any resisting force, the object will accelerate. Symbolically, F equals m times a. Here we have it again. Remember that F is for force, m is mass, a is acceleration. Actually, you can see this a little bit differently right here. I am going to apply a force onto here. Sorry, let me speed this up a little bit. Okay, I'm about to let go of this car. It's got a force acting on it right there. Will be the weight of this. When I let go, the car, will accelerate toward the end. And as you can probably imagine, if I increase the mass of the car, then it will go slower. If I were to increase the weight that's pulling it down, it's going to go faster. These are all things that are predicted by Newton's second law. So here it is mathematically. F equals ma. Now that's linear, meaning more force produces more acceleration. We can also think of this in an inverse fashion. That is to say, if we divide both sides by m, we see that acceleration is inversely proportional to the mass, meaning more mass gives you less acceleration. There is a brand new unit for this. In fact, this is how we define the units of force. It's called the Newton, in his honor, of course. So the SI metric unit of force is the Newton. It is defined as 1 kilogram times a meter per second squared. That works out to be about 0.22 pounds. There are a few problems here that you can think of. If you'd like to, you can pause the video and then you'll see the answers after this. These are fairly simple ones. I want to talk for a couple minutes about a very special type of force, and this is the force that is due purely to gravity. It's called weight. So when an object has mass, as of course any object does, it also has weight, which is a gravitational effect on it. So in other words, weight and mass aren't quite the same thing. Mass is the amount of stuff, but weight is the gravitational effect on that stuff. Therefore, something can have mass, but can in fact be weightless. Imagine if it's in orbit around the Earth, or even if it is freely falling. That is a form of weightlessness, about which we'll talk more a little bit later. So weight is given by F equals ma, but m is the mass and the acceleration is the acceleration due to gravity wherever you happen to be. Now, like I said, this does imply that weight can change. If you are at the moon, your amount of mass is the same, but the g is less. It's about 1/6 that of Earth gravity, and you would weigh 1/6 as much, meaning if you weighed 180 pounds on the Earth, you're going to weigh about 30 pounds on the moon. If you were on Jupiter, you'd weigh over 2 times your Earth weight, close to 2.5 times your Earth weight, if you can imagine that. But of course, you'd look the same. Here's an example. This actually also works at high altitudes. Here, take a look at these three different things that were weighed with the same scale. I'm sure it's my mistake. The same thing weighed 3 different times, 3 different locations. So here we have at 4,500 feet, it's weighing 295.99. If we look at it at 300 feet, that's close to sea level, 295.21, and look at that at the highest one, 294.93. Very measurable effects. Sure, hundredths of a gram, but that, or tenths to hundredths of a gram, but that is measurable. Just for your information, the weight and mass in the imperial units, you're probably familiar with the weight in the English or imperial units, and that's the pound. However, the English unit of mass is something you may have never heard of. It's called the slug. And to find out what it is, you use weight equals mg, take your weight in pounds, and that equals m times g in 32 feet per second squared. So your mass in slugs is your weight divided by 32. Of course, if you want to find your weight in newtons, you first have to convert the pounds to kilograms by dividing by 2.2 and then multiply by g. Okay, as I've said, weight is subject to gravity, but mass is not. Here's another thing to think about, your weight in a moving frame of reference. Does it change in a moving elevator? It certainly does if you are accelerating. If you're moving, either not moving or moving at a constant velocity, that is no acceleration, you're going to read your normal weight if you're standing on a scale. If you are accelerating upward, you're going to read greater than your normal weight, and you can feel that in your knees. If you're accelerating downward, or for that matter, going up, but slowing down, you're going to feel lighter than normal. If you were in free fall, that is what it means to be weightless and also terrifying in that situation. This is also worth thinking about when we talk about falling objects. You know that F equals ma. Therefore, if the falling force is the weight, weight equals ma, or mg equals ma, and therefore g is a for all falling objects. So something like an elephant might be falling, which sounds horrible actually, but it's got a greater weight or greater force pulling down, but it also has a greater mass resisting the motion. That is to say, the ratio of those two, the boy and the elephant falling, is the same, and that ratio is g. Finally, let's talk about the third law. To every action, there is always opposed and equal reaction, where the mutual actions of two bodies upon each other are always equal and directed to contrary parts. For every action, there is an equal reaction. That is, forces exist in pairs. Let me give you some examples. In order for you to walk forward, you have to actually push backward on the earth. Now, you've probably never thought about this before, but think about the mechanics of walking. You're actually pushing backwards. If you try and go forward by pushing forward, well, it's not going to happen. So you can't actually do that. You cannot actually make yourself move forward by pushing forward. Rocket engines push hot gases out of one end, and it's the gases that push the rocket forward. Therefore, rockets can fly in space where there's no air. They certainly can fly where there's no air. And if you were to fire a weapon, the firearm kicks back at you due to the explosion in the chamber. A couple of other examples for you. If you were stepping off of a boat, you are pushing the boat backwards, and the boat pushes you forward. If you and a friend are on skateboards, when one pushes on the other moves back. Okay, this will be continued with some of the mathematical details in the next video.